Hi everybody, today we are going to talk about osmosis and how it affects water potential. So a lot of what we learn is going to be very closely related to osmosis, so make sure you know osmosis well. If you think you may be having trouble with any aspects of osmosis, make sure you go back and watch that video, or you do some practice before you continue on with water potential. So what is water potential? Well, water potential, which is going to be abbreviated with the Greek letter psi, determines the rate and direction of osmosis. So think of this as a more complete answer to what we know about osmosis. Water potential is a tendency of water to leave one place in favor of another. So if you look at the U-tube, the U-shaped tube, on the right here, if you didn't know anything about water potential, you could probably predict that the water is going to move to the right. However, there is another explanation, a more complete explanation for why that happens. So what you learned is still true. We're just learning a little bit more on top of it. Water moves from the solution with a higher water potential to the lower water potential. We always go high to low with water potential. Potential refers to the ability of molecules to move freely. So if you have a high water concentration, then you have high water potential. Water potential is affected by two factors. Those two factors are pressure and the amount of solute. Both of those things affect water potential. For example, imagine a red blood cell was dropped into some distilled water. Well, if we look at what happened in that animation, if you caught it, the red blood cell lysed, right? And that's because water moved in and the cell expanded, and then the pressure of that incoming water caused the cell to break or to lyse open. If a plant cell, though, is placed in distilled water, what's going to happen? Well, water is going to move in, the cell is going to expand. However, we've got a cell wall, which is rigid but somewhat elastic, and that is going to exert a pressure back on the water. And that's going to limit the net gain of water. So both the solute concentration but also the pressure are going to affect water potential here. So think about it. You already know these things. We're just now overlaying it with water potential. So water potential is calculated using the following formula. This is something you should know. It's easy though. Water potential, psi, is equal to pressure potential. So that has the subscript P plus the solute potential. So if you add the pressure potential and the solute potential together, you get the total water potential. Psi, psi P, and psi S all equal 0 in a solution of pure water, so distilled water at atmospheric pressure. What does atmospheric pressure means? That just means that it's an open container exposed to the pressure of the normal atmosphere. We can measure water potential in megapascals. We can also measure it in bars. A bar is approximately an atmosphere. You may remember that measurement from chemistry. And a megapascal is approximately 10 atmospheres of pressure. So bars and atmospheres are roughly the same, and a megapascal is about 10 times more. We're not going to spend too much time worrying about the units. All right, so when we talk about pressure potential, turgor pressure is going to be the force caused by the cell membrane pushing against the cell wall. So think about it pushing out, and then the wall pressure is an equal and opposite force exerted by the cell wall, kind of pushing in. It counteracts the movement of water. And there are other pressures that we're going to talk about on later days: tension, cohesion, atmospheric pressure, root pressure. These are the pressures involved in bringing water up a tree and out of a tree. We'll talk about that more later, though. Don't worry too much about that now. So let's talk about pressure potential. Pressure potential can be negative, it can be 0, or it can be positive. Pure water has a pressure potential of 0. Right? So if you've just got pure water in an open container, the pressure potential is 0. If we're talking about a cell that has plasmolyzed, well, it has shriveled. It basically has a negative pressure potential. In a turgid cell, a full cell has a positive pressure potential. We are usually going to be talking about positive pressure potentials. Usually something exerting or squeezing the water is going to be a positive pressure potential. Increasing pressure raises water potential. All right, a good example is the syringe. If we apply pressure to the water in the syringe, that water wants to move. So when we apply pressure, we are sort of causing an increase in pressure potential because that water wants to go somewhere else. All right, applying positive pressure to the right arm makes the pressure potential higher there. So we've got pure water at equilibrium, everything's equal. If we apply pressure down, then it's going to force the water to the left. That's pretty obvious, right? Pressure is going to move that water. That's pressure potential. Solute potential is different. Solute potential, also called osmotic potential, is determined by the concentration of solute in a solution. Solute potential can be negative, it can be zero if there is no solute, but it can never be positive. Pure water has zero solute potential, and the more solute you add, the more negative the solute potential becomes. So a very hypertonic solution has a very negative solute potential. A hypotonic solution has a less negative, but still negative, but less negative solute potential. And if it's pure water, it has zero solute potential. All right, so overall, when you add solute, you are decreasing the water potential. So that's the effect. When you pour something that isn't water into water, the solute potential goes down. So basically what that means is that when solute is added, the water potential drops. And water will tend to move into that solution. Remember, water is going high to low. So let's look at this as an example. We have our U-shaped, we have our U-shaped tube here. And the U-shaped tube is not equal on either side. The pressure potential of each side is the same because it's open. However, there is more solute on the right, this side, than the left. So if there is more solute on the right, then this is a more negative number. So let's call this negative 10 solute potential. So what's the solute potential on the left-hand side going to be? And we don't exactly know from this picture, but we know that it is a smaller number than negative 10. So instead of negative 10, we know it's still going to be negative, right? It's going to be below 0, but above negative 10. So let's call it negative 5. All right. So water potential moves from high to low. So the bigger number is negative 5. The smaller number is negative 10. So the water is going to move to the right. And that is what we see happening over here. Right? And we see in this picture, this GIF above here, that the water is dissolving the salt in that picture. And this is kind of what's happening. That water, if it's dissolving an ion, it's not really free to move anymore. So we don't consider that free water. So it's not really, that's why it's decreasing the water potential, because the water is still there, but now the water is dissolving solute. And so it's not available to undergo osmosis. All right, solutes have a negative effect by binding water molecules. Adding solutes to the right arm makes the water potential lower there, resulting in a net movement of water to the right. So we added solute to the right arm, and therefore water moved to the right because it had to move from high to low. Right? Solutes and positive pressure have opposing effects. So now look at what's going on. We added solute to the right arm, but what did we also add? We added this plunger. So the plunger, if it is acting an exact opposite to the solute potential, we have a water potential now of 0, right? Because the solute potential and the pressure potential have completely counteracted one another. One is a positive number. One is a negative number, right? So let's start off on the left. We basically have a water potential on each side of 0. So there's no net movement. Now, when we added the solute, we turned this into a negative 10, but the plunger gave us a positive 10. So is the water actually going anywhere? No, because the net water potential is still 0 on either side. This is the effect of a cell wall. Okay, so the standard for measuring water potential is going to be pure water in an open container. That's like nothing, no potential. That is a standard. Pure water in an open container has a water potential of 0. If we add solute, then we reduce that water potential. Water potential is usually going to be negative or possibly 0. And water goes from hypo to hyper. Another way of saying that, and the way you should say it from now on, is a high water potential to a low water potential. Some reminders: water always moves from high to low or hypo to hyper. Solute concentration is related to osmotic pressure. Pressure is related to the pressure potential. Pressure raises the water potential, solutes lower it. And when working problems, use 0 for pressure potential in animal cells and in open beakers. We're never really going to deal with pressure in animal cells. It doesn't happen very often. Open beakers are always 0 as well. And then we already went over this. A bar is the same as an atmosphere. All right, here's that formula again. Water potential equals the pressure plus the solute. And this is just review. You can read this on your own. This last part is the sum. When solute is added, the water potential of a solution drops, and water will tend to move in to that solution. Okay, so here we've got a flaccid cell, and we have put it into pure water, a hypotonic solution. Right? So basically, the water starts moving in, right, until the cell wall exerts a pressure back because there's so much water in. So the influx of water stops when water potential of the cell equals the water potential of the surrounding fluid. And then in a hypertonic solution, the same thing happens. We add it in, water flows out, and it continues to flow out until it has equalized the same water potential in and out of the cell. Okay, you measure the total water potential of a cell and find it to be negative 0.24 bar. If the pressure potential of that same cell is 0.46, what is the solute potential? Try this problem now. Remember, water potential equals solute plus pressure. Give you a minute. Here is the answer. If we do the algebra there, we end up with a negative 0.7 bar for the solute potential. All right. Now, another formula that you should know, this one is always going to be given to you on a formula sheet, is here. This is to calculate the solute potential. So the solute potential is shown with the formula negative I CRT. Now, let's find out what this means. So I is the number of particles the molecule will make in water. So what does that mean for NaCl? You hopefully remember from chemistry, NaCl will dissociate in water, Na will become an ion, Cl will become an ion. So 1 NaCl is going to become 2, it doubles. For things that are covalently bonded like sucrose or glucose, that number is always 1. If it's something like CaCl2, Ca and 2 Cls would give us 3. That's the number of particles. C refers to concentration. This is molarity. R is the pressure constant. We are always going to, if we're using bars, we're always going to use 0.0831. And T, temperature in Kelvin. So make sure you always convert to Kelvin. So the molar concentration of a sugar solution in an open beaker has been determined to be 0.3 molars. That's the concentration. Calculate the solute potential at 27 degrees. Remember, this is sugar. So how many particles will sugar have? We know that sugar is covalent, so that's going to be 1. Round your answer to the nearest hundredth. What is the water potential? All right. Well, if we take negative I CRT, the I is 1. The concentration is 0.3. We've got the R, the constant, 0.0831, and the temperature would be 300 Kelvin, and that has to be negative, so it's negative 0.748 bar. And remember, this is the solute potential, not the overall water potential. All right. If a cell having a molar concentration of glucose at 0.22 molar is placed in a solution of pure 20 degrees Celsius water, what will its pressure potential be at equilibrium? This could be a tough question. So try it out. Just a few hints. What I would do is I would assume that it's being placed in water that is open. And I would also assume that the overall water potential is going to be 0. All right. Okay, so basically the water potential is going to be 0. It didn't mention anything about pressure on the solution. It didn't mention anything about solute because it's pure water. So therefore, we know that the water potential is going to be 0. The solute potential then, so we're using this equation here. So we know that's 0, which is written there. The pressure potential is what it's asking for. So that's like X. And the solute potential we can calculate, negative 1, because it's sugar, negative 0.22. They give us that in the problem. They give us the temp, and they give us the constant. So that means that our solute potential is negative 5.36. And if our total water potential is 0, then our pressure potential must counteract that. So it has to be positive 5.36. All right, we will end here. We're going to do some practice with these calculations, and let me know if you have any questions.